Hi everyone, this is the lecture video on orifices and weirs under constant head. Okay, let's consider orifice under constant head. So an orifice is an opening through which liquids and gases flow with a closed perimeter. So we have here the presence of a wall with the orifice here. So the liquid will flow through this orifice and it has a closed perimeter. So for these two chambers here, we have the airspace of the left chamber subjected to, in general, pressure P sub A, and as well as the airspace in the right chamber subjected to pressure sub B. We will consider a particle with its path, this one, and later on, it will take time, it will reach point 2. So let's consider this as the datum. Then the depth of liquid above point 2, the center of this orifice here is H sub A. Then the depth of liquid in the right chamber is also H sub B. So we will call the distance of point particle 1 from the datum as Z1 in particle 1 to the liquid surface in the left chamber as Y1. So writing energy equation between points 1 and 2, neglecting head loss first so that we can derive the theoretical velocity at point 2. It consists of velocity head at 1, pressure head at 1, plus elevation head at 1 equals velocity head at point 2, pressure head at point 2 plus elevation head at point 2, where the elevation head at point 2 is just 0. Now, pressure at 1 is pressure at A plus gamma specific weight of liquid times Y1. So therefore, pressure head at 1 is equal to pressure head at A plus Y1 after we divide it by gamma. And substituting, so pressure head at A plus Y1, that's the pressure head at point 1 plus elevation head at 1 equals velocity head at point 2. Pressure head at point 2, by the way, consists of, because the pressure at point 2 is pressure at B plus gamma times HB, so the pressure head at point 2 is pressure head at B plus HB. Then elevation head at 2 is 0. So noting that y1 plus z1 in the figure is y1 plus z1 is HA. So replacing it by HA, then equals velocity head plus pressure head at B plus H of B. Rearranging so that in the right side, what remains is this velocity head at point 2. And we will denote the difference between HA and HB as small h, the vertical distance of the liquid surfaces. So velocity head at A plus pressure head at A plus H sub A minus H sub B minus pressure head at B equals velocity head at point 2. So velocity head at point 2 consists of velocity head at 1, pressure head at A, elevation head at A, then minus pressure head at B minus H sub B. So we take note that this velocity head at 1, pressure head at A plus HA is the upstream head. The head here, the energy at the left side, while quantity pressure head at B plus H sub B, so this is minus quantity pressure head at B plus HB, is the downstream head. So the upstream head consists of velocity head at 1, pressure head at A, and elevation head at A. So that's the upstream head, or simply the energy above this datum here is pressure head at A plus HA plus velocity head at 1. While the downstream head consists of pressure head at B and H sub B. So pressure head at B plus H sub B. That's the downstream head. When the area of the reservoir in the left chamber is greater than 16 times the area of the orifice, then so this is the theoretical velocity in general, square root of, from this equation here, square root of 2g cross multiply square root of 2g times upstream head minus downstream head, minus quantity pressure head at B plus H sub B, which is the downstream head. So when the area S, area of the left reservoir, is greater than 16 times the area of this orifice here, then the velocity head of approach is negligible, where velocity head at 1 is the velocity head of approach. Or, in short, if this is the particle, the area of the reservoir is very large, it will take long time before it reaches point 2. So that's why the velocity head at 1 is negligible. If that is negligible, the upstream head consists only of pressure head at A plus H sub A. Then the downstream head consists only of pressure head at B and H sub B. Now, aside from that, when the liquid surfaces A and B are exposed to the atmosphere at the same time, HB is 0. So this situation reduces to this situation here. So we have surfaces exposed to the atmosphere and there is no HB anymore. That the upstream head consists of big H and the downstream head is 0. Or the upstream head consists only of small h, then downstream head is 0, then the theoretical velocity becomes square root of 2g times small h from this original figure if both A and B are exposed to the atmosphere and there's no HB. Or in general, theoretical velocity is square root of 2g times big H, as in this case here. So the actual velocity at the vena contracta of the orifice, which is at point 2, because area at point 2 will reduce because of these particles here coming from here, so the area converges or contracts. So the general formula for actual velocity is introducing a coefficient which is close to 1 but less than 1 from this theoretical velocity. So it becomes C sub V square root of 2g big H. So C sub V, coefficient of velocity, square root of 2gh. This coefficient of velocity is close to 1 but less than 1. And we will define that later as the ratio of the actual velocity to the theoretical velocity. So the actual discharge is area at the vena contracta times actual velocity. So this small a is the area at the vena contracta, which is less than the area of the orifice. Theoretically, it occurs at distance d over 2 from the center of the orifice. And v is the actual velocity. So since actual discharge, so let's now define coefficients here, 3 orifice coefficients, namely coefficient of discharge, the ratio of the actual discharge to the theoretical discharge, and that is less than 1. Then coefficient of velocity, ratio of actual velocity to theoretical velocity, and coefficient of contraction is ratio of area at the vena contracta to the area of the orifice. All these coefficients are less than 1, and we expect that C sub V is the highest among these coefficients, but less than 1. Therefore, substitute into this equation, capital Q is coefficient of discharge, theoretical discharge. So these are the different names for these coefficients. So CQ sub D is equal to C sub C area O times C sub V V sub D. So C sub C area O times C sub V theoretical velocity. So rearranging, CQ sub D equals C sub C sub V times quantity area O V sub D, where area of V sub D is the theoretical discharge. So we can cancel theoretical discharge. So the relationship among these three coefficients is coefficient of discharge is the product of coefficient of contraction and coefficient of velocity. So Q is coefficient of discharge times theoretical discharge, wherein theoretical discharge is area O times theoretical velocity. And since theoretical velocity is in general square root of 2g times big H, remember that big H is upstream minus downstream head, then you just compute for different situations. It will just be H for the simplest case where we have a reservoir and an orifice exposed to the atmosphere. So that's it. Actual discharge is Ka o Tog, so that you can easily recall it. Then let's proceed to the head loss in an orifice so that we can compute the actual velocity, and we will derive formula for head loss in an orifice. So the orifice is installed horizontally, and its energy initially is big H. Because of losses, the jet will rise to a height less than big H, and that difference is the head loss. So the height to which the jet rises is denoted by small h. Therefore, the difference between big H and small h is the head loss in an orifice. So since final velocity 0 equals initial actual velocity v square minus 2gh, so the value of small h is v square over 2g, or actual velocity head. So from the figure, head loss is big H minus small h, and replacing small h by actual velocity head. And since v is c sub v, actual velocity is c sub v square root of 2g big H. So v square equals c sub v square times quantity 2g big H. So v square over 2g is c sub v square big H, and big H is v square over c sub v square 2g, or 2g c sub v square. So replacing v square over 2g, the actual velocity head here, by this equivalent formula. So head loss is h minus c sub v square big H. So the formula for head loss, which is more compact than the other formula, is quantity. It is equal to head times quantity 1 minus c sub v square. Now, instead of this formula, we replace big H by this value, v square over 2g c sub v square minus v square over 2g, factoring out actual velocity head. So the other formula for the head loss in an orifice is quantity 1 over c sub v square minus 1 times actual velocity head. So notice that this formula is similar to the head loss in a nozzle, wherein v here is velocity at the tip of the nozzle. So I hope that you can also recall it. So next, we proceed to, these are the important formulas here. WEIRS under constant head. So we define a WEIR as a hydraulic structure built across an open channel for the purpose, overflow structure built across an open channel for the purpose of measuring the flow rate or the discharge. So we also have rectangular suppressed weir. A rectangular suppressed weir is a rectangular weir, where the width of the channel is equal to the length of the crest of the weir. The width of the channel is denoted by small letter b, while the length of the crest is denoted by L. So this is the weir plate, and it is sharp crested here. This is the head over the weir. This is the channel. Then this is called the nap. So there is air here. Then of course we have liquid not shown. Then the height of the weir is denoted by capital P. The depth of the channel, small letter d. So capital P is the height of the weir. So if you position yourself here, this would be the front view. So because this is the side of the channel and this is the crest, so there will be no contraction. So the liquid will just stick on the side of the channel. So no contraction happens. That's why it's called suppressed wear. Now, this is the strip of the section here. And this is treated as an orifice. So this is the head over the orifice. The center of this strip is denoted by small h since this is capital H. So therefore, this distance is big H minus small h. This is the width of the channel, which is denoted by B, and this is the length of the crest, which is sharp crested. Crest of the weir. And this is the weir plate, normally made of steel, but in the rice fields, it is made of just plywood or any plate. So again, this strip here is treated as an orifice, and the discharge through here is differential Q because it is only a strip which is treated as an orifice. So from this formula, differential discharge equals coefficient of discharge in a weir, then area of orifice, which is the area of this strip, which is LDH, then square root of 2G then times small h. So that's it. So dq equals from this formula from orifice, discharge formula from orifice, but we use it here. This is treated as an orifice, so the discharge is differential Q, coefficient of discharge in a weir, area of orifice, which is LDH, then square root of 2G times head H. So Q therefore is the integral of C square root of 2G integral of area O, which is LDH from the figure. Then what is left in the radical is square root of H. Since L is constant, then we have integral of square root of H dH, or integral of H to the 1/2 dH from 0 to big H limits. So the integral of H to the 1/2 dH is 2/3 H to the 3/2. So the discharge formula for a rectangular suppressed weir would be 2/3 CL square root of 2G big H to the 3/2. Then that's the discharge formula for rectangular suppressed weir, neglecting the velocity head of approach or neglecting the velocity of the channel here, because the velocity here is higher compared to that of the mean velocity in the channel, or velocity of approach, velocity head of approach. So actual discharge is 2/3 CL square root of 2G times H to the 3/2 for rectangular suppressed weir. Then combining this constant 2/3 and square root of 2G, which is square root of 19.62, then we can develop a formula which is easier to recall. Q equals 2.953 L CL H to the 3/2. So that would be the results after we combine 2/3 and square root of 2G as one constant. Then when the velocity head of approach is considered, the formula becomes, so we just replace big H here by quantity H plus H sub V, then raised to 3/2 minus H sub V to the 3/2. So here also, we just replace H to the 3/2 into quantity H plus H sub V to the 3/2 minus H sub V to the 3/2, where in this formula H sub V is the velocity of approach, velocity head of approach, where velocity of approach is equal to discharge divided by width of channel times depth of flow in the channel. Take note, cross-sectional area of the channel is width of the channel times depth of flow in the channel. So that's the definition of V sub A. Then square over 2G, that's the velocity head of approach. So formulas developed by Francis incorporate C, which is slightly greater than 0.6. So And this is by Francis. So by his experiment, so this is empirical formula, but there's a sense, and it becomes 1.84 LH to the 3 halves, neglecting velocity of approach. If the velocity of approach is considered, then we replace H by the same. So 1.84 L quantity big H plus H sub V to the 3 halves minus H sub V to the 3 halves. Then we have rectangular contracted WEIRS. So we use these formulas when in the problem it is stated that we have to use Francis formula. Now rectangular contracted WEIRS, when the width of the channel is greater than the length of the crest, or when they are not equal, the width of the channel is not equal to the length of the crest, then the weir is said to be contracted. So for instance, if this is the side of the channel, a rectangular channel, and we have a weir plate here, so there is water here that flows into this center opening. Naturally, the curve or this water mass will contract, and that contraction here is approximated to be 10% of the head. So that's why this is the length of the crest. It's no longer equal to L, but it is less than L. This is the width of the channel. So this is an example of a rectangular weir that has two end contractions. Now, when one end is suppressed, for instance, this is also the side of the channel, then there will be no contraction here, and there's only one end contraction. So Q becomes 2.953 C L prime H to the 3 halves from this formula here. Or if using Francis formula, you just replace L by L prime, depending on the situations, considering or not considering velocity head of approach. Then Q is also 2.953 C L prime quantity H plus H sub V to the 3 halves minus H sub V to the 3 halves. And L prime here is L minus 0.1 NH, where N is the number of end contractions. So the number of end contractions for rectangular weir is maximum 2, but it can also be 1. When N is 0, it is a suppressed weir, of course. So that's it for rectangular weirs. Let's now proceed to discharge over triangular weirs. So for triangular weirs, if you look at the configuration, there will be no more contraction. So still, we consider the head as big H. And we have here a strip, horizontal strip, that is small h, the head over this strip, which is treated as an orifice again. So this is big H minus small h. Then the length of the water surface is L sub W. So that's dH, that's L sub W. So differential discharge from Kautog formula. So C, area O is length of this strip, which is X, times dH, then square root of 2gh, theoretical velocity. Then we express X in terms of small h by similar triangles. So Q equals C square root of 2g integral of X square root of h dH by similar triangles. X as to big H minus small h equals LW as to big H. So X is LW over big H times quantity big H minus small h. So substitute into that formula. So Q equals C square root of 2g integral from 0 to big H of LW over big H times quantity small h minus big H minus small h from X, then square root of h dH. So because all of these are constant, so the integral of the first, which is constant big H, h to the 1/2 is 2/3 big h to the 3/2, then minus h square root of h is h to the 3/2, so the integral is 2/5 h to the 5/2. So Q equals c square root of 2g LW over big H times 2/3 of big H to the 3/2 minus 2/5 of small h to the 5/2 from 0 to h. So it becomes 2/3 of big H to the 5/2 minus 2/5 of big H to the 5/2, then divided by big H. So the formula for triangular WEIRS, like this one, is 4 over 15 c square root of 2g LW h to the 3/2. That's for triangular WEIRS in general. Now for V-notch WEIRS, when you say V-notch, the shape is an isosceles triangle such that the angle that one side makes with the vertical is theta over 2, and the whole angle here is theta. So all you have to do is we multiply this formula by 2h over 2h. So that's LW over 2, LW over 2. So 4c square root of 2g LW over 15, then h to the 3/2, this is for triangular WEIRS. Then we multiply 1, which is represented by 2 big H over 2 big H. And we take note that the ratio of LW over 2 over H is tangent theta over 2. So replacing LW over 2H by tangent theta over 2. So the formula for V-notch WEIR becomes 4 times 2 is 8 over 15 c square root of 2g tangent of theta over 2 times big H to the 5/2. So this is the discharge formula, actual discharge formula for a V-notch WEIR, or a WEIR, triangular WEIR that is isosceles triangle. So when theta is 90 degrees, tangent of 90 over 2 is tangent 45, which is equal to 1. And combining with C, which is above, slightly above 0.6, the formula becomes, it's easy to remember, 1.4 big H to the 5/2. So combining everything, square root of 2g, 8 over 15, and c, which is slightly above 0.6, then the empirical formula, which is for 90-degree V-notch WEIR, is 1.4 h capital H to the 5/2. As simple as that. We then have to memorize WEIR formulas and coefficients. One coefficient of discharge formula for sharp crested WEIRS is given by 0.611 plus 0.075 times quantity big H over height of WEIR P. So, and that is for sharp crested WEIRS. Also for sharp crested WEIRS, we call this Ribok formula. Considering surface tension effects, the second term is by surface tension effects. So the coefficient of discharge is 0.605 plus 1 over 1000 big H plus 0.08 quantity H over P. So this term considers surface tension effects. That's also for sharp crested WEIRS, and we call that Ribok formula, considering effects of surface tension. This is accurate if the height of the WEIR ranges from 0.1 to 1 meter, and the head over the WEIR ranges from 0.025 meter to 0.6 meter. Then discharge formula for broad crested WEIR, 0.605 over quantity 1 plus H over P raised to 0.5, or 0.65 over square root of quantity 1 plus H over P. Then when the value of C is square root of 3 over 3, or 0.5774, then there is a direct formula for broad crested WEIR, 1.705 LH to the 3/2. So that's the actual discharge for broad-crested weir when the value of C is square root of 3 over 3. So we have here discharge formulas for submerged weir. So it is equal to Q, actual discharge Q, quantity 1 minus H2 minus H1 raised to 1.5, then closed raised to 0.385, where Q is 2.953 CL H1 to the 3 hubs, just like for rectangular weirs. So this is the definition of H1. H2 would be this. So that's the height of the weir, P. That's the depth in the channel, and this is the submerged weir, and that's H2. So from this formula here. But in most cases, C is given unless otherwise, because these are empirical formulas, difficult to memorize. But you have to memorize, of course. It might be not given and you're asked to use Reebok formula, or for this C here for sharp crested weirs. Then this is the broad crested weir, just like the crest of a dam. So that's it for broad crested weirs. So lastly, for the general shape weirs, the discharge formula, such as this, would be dq equals kautog C, where area O is xdh, then square root of 2g small h. That would be the starting equation. So that q is integral of c square root of 2g, c square root of 2g integral from 0 to big H of x square root of h dh. For this integral to be feasible, then x must be a function of small h and other given information here by geometric relationships. Then for a weir that is an isosceles trapezoid, when the slanted side, the slope of the tangent of the angle that the slanted sides make with the vertical is 1/4, then it is called Sepuleti weir. So actually, Sepuleti weir is an isosceles trapezoidal weir which replaces the two-ended contracted rectangular weirs as before. Now, when tangent of theta over 2 is not equal to 1/4, then that isosceles trapezoidal weir must be treated as rectangular weir plus the V-notch weir. And you can use the discharge formula for rectangular and for V-notch weir so that you can derive the discharge formula for an isosceles trapezoidal weir. And the direct formula for the Sepuleti weir is 1.859 LH to the 3 hubs, where L is the length of the crest of the Sepuleti weir. And this is what I told you, that for two-end contracted weirs, so this becomes the sloping side of the trapezoid. Can you see this trapezoidal isosceles trapezoidal weir? When the angle that this side makes with the vertical tangent theta over 2 is 1/4, then it is a Sepuleti weir. If not, then you just treat that as trapezoidal weir. Then the discharge is Q of a rectangular weir plus these two combined V-notch weir. So that's all for weirs and orifices.